Okay, so good evening and welcome all of you for the fifth live session for the NPTEL course Introduction to Semiconductor Devices. As you know, the course tutor is Professor N.K. Imani from IIT Hyderabad, and I am your PMRF TA for conducting these live sessions, Samadhan Kamble. I am a PhD scholar at IIT Madras. I work in experimental high energy physics in the CMS experiment at Large Hadron Collider. Okay, so as you are familiar by now that the plan for these sessions is quite simple. I'll briefly discuss the lecture content of this week uh, in less than 10 to in about 10 to 15 minutes. It will give you a brief refresher, and then we will move to the assignment problems, which are primarily from the previous courses offering, and also some gate uh, yeah also some gate exams questions relevant to these particular course content I have included. So needless to say that these are quite beneficial for your current assignment solving as well as for the end semester examinations. So without further ado, let's get started with our short recap first. Okay, so this week was basically devoted to modeling the steady state response of a PN junction diode. A qualitative description of the diode operation using the band diagram was given, and various parameters characterizing the forward and reverse bias for an ideal diode was derived. Some non-idealities resulting from approximations used to derive the diode characteristics were also described, and a fair amount of attention was given to the different processes and their impact on diode parameters. Finally, the temperature dependence of the diode parameters was also mentioned, along with its impact on the different parameters like threshold voltage, reverse saturation current, and reverse breakdown voltage. Also, I have summarized all these in the in this slide. You can see here. So just consider the PN junction with a forward bias voltage applied. Uh, the potential barrier of the PN junction is lowered when a forward bias voltage is applied, and which allows electrons and holes to flow across the space charge region. And when holes from the P region across the space when when holes from the P region across the space charge region into the N region, they become excess minority carrier holes and are subject to the excess minority carrier diffusion, drift, and recombination processes, as we discussed in the previous week. Likewise, when electrons from the N region flow across the space charge region into the P region, they become excess minority carrier electrons and are subject to these same processes like diffusion, drift, and recombination processes. So let us first consider the p-type PN junction with forward biases. So the forward bias in which the applied voltage V applied is positive, so V applied is more than 0, and the majority carriers diffuse into the depletion region, which decreases the net space charge. So the net space charge here gets reduced, and hence the depletion width also gets reduced. So we got these relations for the minority carrier concentrations at the edge of the depletion region in forward bias. So it is given by these two relations. So the minority carriers at the edge, like minus xp here, and the minority carriers holes in the xn, that is here, that is at the edges, is given by the equation number 1. Also, the law of the junction is the NP product, which is valid across the junction, and it is given by this relation. So this can be simply derived using the non-equilibrium carrier densities. So N and P are non-equilibrium carrier densities, which in the in as a function of the Fermi energy are given as N is equal to Ni exponential of EFN minus EFI by kT, and similarly the P is given as Ni exponential of EFP minus EFI minus EFP by kT. So if you just multiply these two, so the product will give you the law of the junction, and it will be function of EFN minus EFP. EFN minus EFP is nothing but our built-in potential QVA. So that's how we get our NP product. Going to the second slide for the summary. Here we consider the reverse bias PN junction, and in the reverse bias case, the voltage applied is negative and the majority carriers move out of the PN junction, and hence the net space charge, so V applied is negative and the net space charge increases, and hence the depletion width, that is phi depletion, also increases. Also the width of the depletion region in the reverse bias is given, which is as a function of the applied reverse bias voltage and the built-in potential, and also the carrier concentrations, which are the dopants, which are acceptors and donors. Also the maximum electric field in the reverse bias is given by this particular relation, which is also a function of the built-in potential and the applied reverse bias voltage. Going to the third slide, the junction capacitance, the concept of junction capacitance is introduced here. So since we have a separation of positive and negative charges in the depletion region due to the reverse bias, a capacitance is associated with the PN junction, and just consider an abrupt PN junction and it is biased with reverse bias voltage VR. The depletion width across the junction increases and forms a capacitance known as the depletion capacitance or a junction capacitance. So the C depletion is denoted generally as Cj, and it is in units of picofarad per centimeter square. So it is capacitance, general capacitance per unit area. So it is given by this relation Cj. We know that capacitance is dq by dp. Will get so the capacitance is a function of the depletion width, and in turn the width is function of the built-in potential and the applied reverse bias voltage. So our capacitance, the junction capacitance, is also function of the reverse bias voltage and the built-in potential. So we need to keep in mind that the space charge width is a function of the reverse bias voltage, so that the junction capacitance is also a function of the reverse bias voltage applied to the PN junction. Okay, so this also forms an important criteria of a device called as the varicap or the voltage controlled capacitance. As you can see here, the capacitance varies inversely over the applied reverse bias voltage. So the capacitance can be controlled, the value of capacitance can be controlled by using different values of the reverse bias voltages. So this also forms a device also called as the varicap, which basically works on the principle of junction capacitance in the reverse bias case. Okay, also we considered the reverse saturation current variation with respect to the temperature. So the reverse saturation current almost doubles for every 10 degrees centigrade rise in the temperature. So this is approximately the relationship for the reverse saturation current as a function of temperature rise. Then we finally moved to the concept of junction breakdown. So in the last section, in the last weeks, in fact, we determine the effects of applying a reverse bias voltage across the PN junction. However, the reverse biased voltage may not increase without limit. At some particular voltage, the reverse biased current will increase rapidly, and the applied voltage at this point is called as the breakdown voltage. So there are two physical mechanisms which give rise to the reverse bias breakdown in PN junctions. So these are the Zener effect and the avalanche effect. So the Zener effect, which gives rise to Zener breakdown, occurs in highly doped PN junctions through a tunneling mechanism. And in a highly doped junction, the conduction and valence bands on opposite sides of the junction are sufficiently close enough during the reverse biasing that the electrons may tunnel directly from the valence band on the p side into the conduction band on the n side. So this gives rise to the Zener effect, forming the Zener breakdown. On the other hand, the avalanche breakdown process occurs when electrons and holes moving across the space charge region acquire sufficient energy from the applied electric field to create electron hole pairs by colliding with the atomic electrons within the depletion region. So this is the process of avalanche effect giving rise to avalanche breakdown, which is an important process in the junction breakdown. Okay, so I think this forms this concludes the summary for this particular week. So let us directly move to the assignment problems. Okay, so this is the common data for question number 1 to 3. So the data I'll read out for you is: the plot is given and it shows the carrier concentrations in a PN junction at room temperature. Only the quasi-neutral N side of the junction is shown. So the N side is only shown here, P is not shown. And we need to answer following 3 questions like 1, 2, 3 based on this particular information. Okay, so let us go to the question number 1. Let's go to this question first. The intrinsic carrier concentration Ni in per centimeter cube is they have asked. So we know that the intrinsic carrier concentration is basically Ni is equal to under root of the Nn and Pn. So under the equilibrium condition, we know that under equilibrium, the negative charges on the N side is given as 10 to the power 16 per centimeter cube, and the positive charges on the N side is given as 10 to the power 10 per centimeter cube. So as you can see in the figure here, the concentrations for the Nn and Pn in the equilibrium condition are given. So if you just substitute these values here, we'll get the value of Ni as 10 to the power 26, that is 1 into 10 to the power 13 per centimeter cube. So the answer is this. So let us go to this question. So it is a little conceptual. So they have asked is the shown diode in the previous slide is in which biasing? Is it in forward bias or is it in reverse bias? And also the reasoning they have asked here. So as you can see in the carrier concentration figure here, that the excess minority carriers, so in the N side, the excess minority carriers are holes. So Pn denotes the positive charges, which is nothing but holes, and which indicates that it is in the forward biasing case. So the minority carriers which are excess on N side indicates it is in the forward biasing case. So which corresponds to this option. So the diode is in forward bias as there are excess holes on the N side. So let us move to the last question based on the common data. So the question is, the magnitude of the applied voltage, that is VA, is given by what value? So the hint is we can use the law of the junctions and calculate the Ni in the quasi-neutral region. Okay, so the law of the junction, as I have shown in the summary slides as well, I'll just write out here. Law of the junction is Pn at xn, that is at the edge, is given by Pn naught exponential of QVA by KT. Okay, so we know that the Pn at the edge is given by 10 to the power 14 per centimeter cube, and the Pn0, that is the equilibrium concentration, is 10 to the power 10 per centimeter cube. So let us just simplify this. We will have 10 to the power 14 by 10 to the power 10, that is 10 to the power 4. 10 to the power 4 is equal to exponential of QVA by KT. So just let us take a logarithm on both sides. We'll have QVA by KT is equal to logarithm of 10 to the power 4, and we know that the KT by Q value for the temperature 300 Kelvin, so we can just substitute here and we'll get the value of VA. So VA is nothing but 0.0259, which is the value of KT by Q for temperature 300 Kelvin times ln of 10 to the power 4, and this will give you the applied voltage we applied as 0.2385 volt. So the answer for this question is option D. Okay, so let us move to question number 4. Okay, so the question is also quite simple but little intimidating. A silicon PN junction has impurity doping concentrations. So the impurity doping concentrations are given Nd and Na. The minority carrier concentrations at the edges of the depletion region for an applied bias of 0.55 volt. So the applied bias is also given and the impurity doping concentrations are given. We need to calculate the minority carrier concentrations. Okay, so we know that using the law of the junctions, so the minority carrier concentrations Pn at xn is given as Pn naught, that is at the equilibrium, exponential of QVA by KT, and similarly the NP at minus of XP, that is at the edge, is also given by exponential of QVA by KT. Okay, so now let us first find out the PM naught and NP naught values, so that we can substitute and get the values of the impurity minority carrier concentrations. So we also know that for the N side, PM naught is nothing but the intrinsic charge carrier concentration squared by the donor concentration, and if we just substitute the values here, we will get 2.25 times 10 to the power 20 intrinsic charge carrier concentration squared divided by the donor concentration 2 times 10 to the power 15 will give you the value of Pn naught as 1.125 times 10 to the power 5 per centimeter cube. Okay, similarly we can find the value of, for the P side, we can find the value of Np naught. which is again Ni square over N acceptors in this case. So 2.25 times 10 to the power 20 divided by the acceptor concentration given as 8 times 10 to the power 15. So NP naught is simply 2.8125 times 10 to the power 4 per centimeter cube. Okay, so now we can just substitute the values of NP naught and PM naught in these equations. So we'll have Pn xn is equal to 1.125 times 10 to the power 5 times exponential of applied voltage is 0.55 by kT by Q for the 300 Kelvin is this much, so 0.0259. If you just calculate it, we will get the value of the minority charge carrier concentrations on the N side as 1.88 times 10 to the power 14 per centimeter cube. And similarly, if you substitute the values of NP naught and VA in this equation, we will get the value of NP at minus XP as 4.69 times 10 to the power 13 per centimeter cube. So the option with these values is this here. So these are the values of the minority charge carrier concentrations at the edges of the depletion region. Okay, so let us go to the question number 5. Okay, so question number 5 is also a common data question, in which the common data is as follows. Considering an uniformly doped gallium arsenic p-n junction at T is equal to 300 Kelvin, the ratio of the junction capacitance at zero bias, so the capacitance when there is no applied voltage is Cj0, and the junction capacitance when there is applied reverse bias voltage of 10 volt is Cj10, and that ratio is 3.13. Under the reverse bias, the depletion region width on the P side is 20% of the total space charge width. So this is the information. So the question number 5 is, the built-in voltage VBI is, okay, so the built-in potential is asked. If you go to the summary slides on the here, you can see that the junction capacitance varies inversely with square root of the applied reverse bias voltage and the built-in potential. So we can use this particular relation. Okay, so we know that the junction capacitance varies as 1 over under root of V built-in plus the V reverse bias applied. So we have given the ratio, that is Cj for no bias voltage applied and Cj when there is a voltage reverse bias voltage applied of 10 volt, and that ratio is given as 3.13. So using this relation we can equate it to VR plus VBI divided by VBI, because VR in this case is 0. Okay, so just substitute the value of VR, that is 10 volt. It is simply 10 plus VBI by VBI. Okay, so it is a simple calculation now. If you just calculate it, we will get the value of built-in potential V built-in as 1.136 volt. Okay, so just using the fact that the uh, junction capacitance varies inversely as inversely with square root of the built-in potential and the applied reverse bias voltage, we calculated the built-in potential. Now let's go to the question number 6, which is also based on this data. So the question is, the doping concentrations Na and Nd are asked. So for this we know that once we have the built-in potential, we can recall one formula for the built-in potential, that is V built-in given as Kt by Q ln of Na times Nd over Ni square. So we need to find out Na and Nd. So built-in potential in terms of Na and Nd is given by this particular relation. We saw it in the previous week, but here we need to determine both Na and Nd. So here we can use one piece of information given here, and that is the under reverse bias condition, the depletion region width on the p side is 20% of the total space charge width. So what they have said is that the xp value, that is depletion width on the p side, is 20% of the total depletion width. That means the remaining depletion width, that is depletion width on the n side, will be 0.8 of the total depletion width. Okay, also we have the equilibrium condition that xp times Na is equal to xn times Nd. So if you just substitute this piece here, we'll get the relationship between Na and Nd, and that is simply Na is 4 times Nd. So we can use this relation in this particular equation, and we can determine one of the value, and then we can using this particular relation we can find out the other. So we know that the Kt by Q is also known to us, that is 0.0259 times ln of, let us substitute the value of Na, that is 4 times Nd. So we will have 4 times Nd squared divided by Ni square. Ni is given as 2 times 10 to the power 16, it's squared. So if you just solve for Nd, we can substitute value of built-in potential, V built-in, that we calculated, that is 1.136 volt. We will get the value of Nd here, and that value is Nd is equal to 3.34 times 10 to the power 15 per centimeter cube. And if you just substitute the value of Nd here, we'll get the value of Na as simply 4 times of this value, that means 4 times 3.34 times 10 to the power 15 is nothing but 12.56 times 10 to the power 15 per centimeter cube. So we have the values of Na and Nd, as 12. If you can just take the approximations, the closest answers are 12 into 10 to the power 15 per centimeter cube and 3 into 10 to the power 15 per centimeter cube for the values of Na and Nd respectively. Okay, so let us go to question number 7 now. Again, question number 7 to 10, these are the common data questions. Consider a uniformly doped silicon PN junction with doping concentrations Na and Nd given as these numbers. The cross-sectional area is also given, the cross-sectional area of the junction given as 2 times 10 to the power minus 4 centimeter squared, and the applied reverse bias voltage is given as 2.5 volt. We can use the value of Ni, epsilon naught and Kt as written here. So let us go to question number 7. So the question number 7 is the built-in voltage of the PN junction is asked. So we know a simple formula for built-in potential. I have written it like quite sometimes. So V built-in is nothing but KT by Q ln of Na times Nd over Ni squared. So if we just substitute all these values, 0.0259 ln of Na is 2 into 10 to the power 17 times 4 into 10 to the power 16 divided by Ni, which is 1.5 times 10 to the power 10 whole squared. We'll get the value of built-in potential V built-in as 0.81 volt. Okay, so this was quite simple. Let us go to question number 8 based on this data. Here they have asked the width of the depletion region in micrometers. So again, if you just go to the recap slides, the built-in the width of the depletion region is given by this particular formula. So we can just use this formula straightforward and calculate the depletion width. So W, which is the depletion width, is given as 2 times the epsilon of silicon in our case divided by the whole Q times Na plus Nd over Na times Nd times the reverse bias voltage applied plus the built-in potential. We calculated the built-in potential in the question number 7. So if you just substitute all those values like the epsilon for silicon given here, the built-in potential that we calculated 0.81 volt, and the values of the Na and Nd, which are the extrinsic concentrations, will get the depletion width as 0.36 times 10 to the power minus 4 centimeter. So in micrometer it is simply 0.36 micron. So the answer is A here. Okay, so let's go to question number 9, which is also based on the common data. The maximum electric field in the region, in the depletion region, is asked. So the maximum electric field, we also have that formula in the recap slide. I'll write it down for you here. So E max is simply the 2 times V built in plus the reverse biased applied voltage divided by the depletion width. So if you just substitute it, you get 2.5 plus 0.81 the built-in potential times 0.36 times 10 to the power minus 4 centimeter. So we'll have E max is nothing but 1.84 volt per centimeter times 10 to the power 5 actually. Okay, you just need to calculate this simply. We'll get the value of the maximum depletion, maximum electric field in the depletion region as 1.84 times 10 to the power 5 volt per centimeter. Okay, so let us go to the last question based on the data given in the previous slide, and that is the junction capacitance in the picofarad is asked. So if you just review the equation number 10 in the recap slide, we'll have the depletion capacitance or the junction capacitance given as epsilon silicon by the total depletion width. So if you just substitute 11.9 times 8.85 times 10 to the power minus 12, sorry, 10 to the power minus 14, it is in centimeters, divided by the depletion width in the centimeter, that is 0.36 times 10 to the power minus 4. We will get the capacitance, that is junction capacitance, as it will be in the capacitance per unit area. We need to find out in the capacitance units, so we also need to multiply it by the area. So area in our case is given as 2 times 10 to the power minus 4 centimeter. So it is indeed area given as 2 times 10 to the power minus 4 centimeter. So we'll have our depletion capacitance in the units of picofarad as 5.85 picofarad. Okay, so this was the last question based on the common data. So the answer for this question is option B. So is there any doubt in this particular question? There were 4 questions based on this data, or in any previous question. If not, I can move to the final couple of questions. So these are a couple of questions. Yeah, exactly. Yeah, do you have any doubt?
The mathematical value, can you say, sir, for
For what?
that question? Width of the P, N type is more than 20% times P. Sorry, the P type width is 20% more than the width of that problem.
Okay. So the
P
problem
type
is
has 20% more than the width.
this problem.
Yeah, exactly.
Yeah. So this is the. So what do you want for this question?
Regarding the calculation, sir, how this 11 1 11
Sorry.
1.136.
Yes, that is the built-in potential that we calculated in the previous problem. So the built-in potential is calculated in question number 5 using this particular relation, and that built-in potential we are using in the next question. So we have this particular relation. So once we know the built-in potential, this value, and Ni is also given, that is intrinsic concentration, we can find the values of Na and Nd. So that thing we have used.
So overall 4 ND square by 4 divided by 4 into
Yeah.
10
So
power 32 is
sorry.
that calculation. Can I say exactly the right hand side and left hand side, sir? For under 1.118 into 10 power 9, 10 power minus 10 power 19 is equal to 4 into ND square by 4 into 10 power 32.
Yes. So yeah, it is simply
So,
we can rearrange. For example, if 0.259 will go here, we can apply the exponential on both sides. So ln will get cancelled. So exponential of 1.136 divided by 0.0259, which is will be equal to 4 times nd square by this particular value square. So we can find the value of nd like simply.
sure, sir. Sure. Thank you, sir. That's what the problem. Thank you.
Okay. Okay. So I'll go to Okay, so I'll go to a couple of last questions. These questions I have taken from previous GATE exams. Again, relevant for this particular week's content, obviously. So this particular question appeared in EC GATE 2018. So the question is as follows: a PN step junction diode with a contact potential of 0.65 volt has a depletion width of 1 micron at equilibrium. The forward voltage in volt at which this width reduces to 0.6 micrometer is. So the forward voltage is asked for which the width reduces to 0.6 micron from 1 micron. Okay. So for this question, we know that the built-in the depletion width, which is given by this particular relation, 2 times epsilon of silicon divided by the charge times Na plus Nd divided by Na times Nd times the built-in potential minus the phi forward bias. So this is the equation of the depletion width in the forward bias case. Now we can see that all these parameters are constant, and what they have done is they have just asked us to calculate the value of the forward bias voltage for which the depletion width reduces. So we can simply use the thing that the depletion width varies with PBI minus VFB. Okay, so when there was no forward biasing, that is VFB was 0, the depletion width was, we can denote it by W0, was 1 micron. Okay, so what they have said is a PN step junction diode with a contact potential of 0.65 volt has a depletion width of 1 micron at equilibrium. So this is one piece of information. So we can substitute the values of W's for two cases. So we'll have one relation, W in the case of forward bias voltage applied, and W when there was no forward bias voltage, that is W0, is simply VBI minus VFB by VBI. In this case, the VFB is 0. So WFB is 0.6 micron, as you can see here. So 0.6 micron divided by 1 micron is V built-in potential given as 0.65 minus VFB by 0.65. So if you just do this simple algebra, we'll get the value of the forward bias applied voltage, which reduces the width from 1 micron to 0.6 micron as 0.416 volt. So the approximate answer is 0.42. Okay, considering it was understood, I'll move to the last question. Okay, so this is also a gate question. It appeared in EC Gate 2017. The question is as follows. As shown in the following figure, this is an abrupt PN junction diodes are fabricated with uniform donor doping concentrations ND1 and ND2, these values, in the N region of the diodes, and uniform acceptor doping concentrations, that is Na1 and Na2, in the P regions of the diodes respectively. Also assuming that the applied reverse bias voltage is much higher than the built-in potential, the ratio of C2 by C1 is asked. The ratio of the junction capacitance of the reverse bias capacitance for the same applied reverse bias is. Okay, so we know that the junction capacitance is simply the epsilon for the silicon divided by the built-in potential in terms of farad per centimeter square. Okay, also we know that the depletion width is directly proportional to the square root of Na plus Nd times the product of Na and Nd. You can see it in the recap slide here. Okay, so we can simply use this fact and we'll get the ratio of the junction capacitance, that is C2 over C1, which will be equal to W2 by W1. So using this particular proportionality, we can write it simply as Na1 plus Nd1 divided by Na1 times Nd1 divided by Na2 plus Nd2 divided by the product of Na2 and Nd2, and the whole is raised by half, that is, it is in the square root. So if you just substitute all these values of Na1, Nd1, Na2 and Nd2 given in the problem here, we can get the ratio of the capacitance, the junction capacitance. Let me just substitute it for you. So 2 times 10 to the power 14 divided by 10 to the power 18, sorry, 10 to the power 28 divided by 2 to the power 2 times 10 to the power 16 divided by 10 to the power 32, and whole it is in the square root. So we'll get the value of C2 over C1 simply as 10. If you just calculate this algebra, you will get the ratio of the C2 by C1, that is the reverse bias capacitance for the same applied reverse bias voltage, as 10. Okay, so the questions are over, but I think we have a few more minutes, so I think I'll go to one more question. Let us go for this question. This question I have taken from the Niemann's book. So the question is as follows: determine the change in the forward bias voltage on a PN junction with a change in the temperature to maintain a constant diode current. Okay, consider a silicon PN junction initially biased at 0.6 volt at T is equal to 300 Kelvin. 0.6 volt at T is equal to 300 Kelvin. Assume the temperature increases to T is equal to 310 Kelvin. Now calculate the change in the forward bias voltage required to maintain a constant current through the junction. Okay, so this is about the temperature dependence. So the forward bias current can be written as the forward bias current can be written as J, which is directly proportional to exponential of minus Eg over kT times exponential of QVA by kT. Okay, now if the temperature changes, we may take the ratio of the diode currents at the two different temperatures, and that ratio is simply J2 over J1, which will be equal to exponential of minus Eg by kT2 times exponential of QVA2 by kT2 divided by exponential of minus Eg by kT1 times exponential of QVA1 by kT1. Okay, so if the current is to be held constant, that is the condition, then J1 would be equal to J2, and we must have then the condition is J1 is equal to J2. So for that we'll have simply, if you just do the simplification, you'll get Eg minus EPA2 is substituted for a value of Q over KT2, which will be equal to Eg minus E times VA1 over KT1. So we know that for a T1 is equal to 300 Kelvin and T2 is equal to 310 Kelvin, the Eg is simply 1.12 electron volt and VA1 is 0.6 volt. So we can substitute the value of Eg, T2, T1 and the Boltzmann constant, and we can find out the value of VA2. So it will be simply 1.12 minus VA2 divided by 310 equal to 1.12 minus 0.6 over 300. So the k is cancelled, and we'll, after the simplification, we'll get the value of VA2, the forward bias voltage required to maintain a constant current through the junction, as 0.5827 volt. Okay, so we can see that the change in the forward bias voltage is about minus 17.3 millivolt for a 10 degrees centigrade temperature change. Okay, so this brings me to my final slide. Thank you everyone for joining live for the live session number 5 for the week 5, and I hope to see you in the next live session, that is live session number 6, scheduled on the 2nd September Friday at 6 p.m. Meanwhile, you can also check out the recordings of these live sessions that I'll upload on my YouTube channel, so that in case you did not follow something during the live session, you can always go back and see it. And yes, so also you can go to the discussion forum on the NPTEL course site and also raise questions there. Thank you again for joining, and I hope to see you in the next live session. Thank you. Have a nice weekend. Bye bye.